This video is going to talk a little bit about weak acids and bases. We spent some class time talking about reviewing grade 11 and looking at some strong acids and bases and calculating pH and calculating your hydrogen and hydroxide ion concentrations. We also talked about what weak acids and bases were, and we said that we know that they have an equilibrium and they don't completely ionize when they're in solution. So what we're going to do now is actually look at some calculations with weak acids and bases. So, measuring the strengths of weak acids, we use something called Ka. The ionization of weak acid is not complete. And we know that because we talked about it yesterday. We talked about how only some of it will actually ionize, and it's usually a very small percentage. So, since this is an equilibrium, the extent of ionization can again be represented using the equilibrium constant. And we call it Ka, again, because in this case we're referring to an acid. So if I use this, so this is acetic acid here. Notice I didn't include H2O in my equilibrium expression because that's a liquid and there's no concentration for water. Okay, so I again put my reactants divided by my products, and that's basically it. So that's our expression for Ka. So that's what we're going to use for the rest of the video. So how do we actually measure the strength of a weak acid? How do we know how strong it is? Well, basically, a strong acid will have a larger Ka and a weaker acid will have a smaller Ka, so we can compare values and figure that out, okay? So in this case, this is our acetic acid. We know it's a weak acid. It doesn't completely ionize and it doesn't completely split apart into its ions. And if we look at its Ka value, which again, there is a table in the back of your text which gives you Ka values for some common weak acids. You can see the Ka value is quite small, 1.8 times 10 to the negative 5, okay? So that's basically where you're looking at. So if we compare it to nitrous acid, HNO2, it's a little bit weaker than nitrous acid, but it's a bit stronger than hydrocyanic acid. So how do we actually calculate Ka? Let's do an example. So here's an example. Formic acid, HCHO2, has a concentration of 0.1 molar. And the pH is 2.38 at 25 degrees Celsius. Calculate the Ka. So here's my equilibrium expression. We know the HCHO2 will split up into its ions, H plus and CHO2. So my initial concentration that I started off with, I gave it to you in the question, was 0.1 molar. My initial concentrations of my H plus and CHO2 starts off at 0 before it actually ionizes. So that means that I know the reaction is going to shift towards the products, and these two values are going to increase by X, and my initial value is going to decrease by X. So then I just have to calculate my Ka, so I need my final equilibrium concentrations. Well, I actually give that to you because I've given you the pH. So remember that if I give you 10 to the negative pH, that can give you your hydrogen ion concentration for this acid. So when I do that, if I do 10 to the negative 2.38, that equals 0.0042. So that's my hydrogen ion concentration, which means 0 plus X is 0.0042. And again, because my H plus and CHO2 is in a 1-to-1 ratio, this is also 0.0042. So you can write that in. Now I can also figure out, if I know that X is 0.0042 molar, I can do my equilibrium expression for the formic acid. 0.100 minus 0.0042. So my final equilibrium of my acid there is 0.10. Oh, that's wrong. Sorry. I did a mistake on my calculation there. So, 0.0958. So now I'm going to do the actual Ka expression in blue. So in this case, my Ka expression is H plus times CHO2 minus all over HCHO2. So now I just plug in my numbers from my ice chart, and I end up with 0.0042 times 0.0042 divided by 0.0958. And I get a Ka value of 1.8 times 10 to the negative 4. So again, a small Ka value indicating we do have a weak acid. Okay. If I want to calculate the pH for weak acid solutions, you basically have to do the opposite of what I just gave you. So I have to give you Ka, and you have to sort of work your way backwards. So we're going to go through an example of that. So step 1 would be to determine the relevant chemical equation and find the Ka values. So if this is my question, find the pH of a 1 molar solution of acetic acid in water. My relevant chemical equation is my acetic acid breaking apart into H plus and CH3COO minus. Okay, and I know I can look up the Ka of that acid in the back of the textbook. It's 1.8 times 10 to the negative 5. So again, I got that from the back of the textbook. So now I've identified all my species. I'm going to summarize the changes in an ice chart and then calculate my value for X. So in my ice chart, oh, I don't have a lot of space to write this in here. My initial concentration of my, I'm not going to write out all of, I'll just do my 3 columns sort of that way. So my initial concentration was, oops, not 0.1, 1 molar. 1.00, and my initial concentrations of my products were 0. So I know this goes down by X, this goes up by X, and this goes up by X. So I end up with 1.00 minus X, and X, and X. Nice thing about this one is, again, I can use the 100 rule. So this here, I can use the 100 rule and eliminate that X. So when I get my Ka expression, it's H plus times CH3COO minus all over CH3COOH. And I can plug in my numbers from my ice chart. So I have X times X, which will end up being X squared, divided by 1, equals, and I gave you the Ka, or you looked it up in the back, 1.8 times 10 to the negative 5. Okay, so when you rearrange your equation and you solve for X, you should get that X is 0.004. So that, if you look back up to your ice chart, is also your concentration for your H plus. So now you can do your pH equation, negative log of the concentration of H plus, and you get your pH is 2.37. So that's a simple way to sort of look at calculating Ka. Oh, you know what? I had another slide to show you step 5. Oh, no, I didn't. There we go. Sorry. So again, your side note, using your approximation to avoid quadratic equations. The second you have a quadratic, always check to see if you can use your 100 rule. So for any ionization acid, this is going to be your Ka expression. Okay, so you'll always have sort of 2 X's on the top, then you'll have your initial concentration of HA minus X. And that ends up giving you a quadratic. But look here, if Ka is small, X will usually be small as well, because not much ionization of the acid will occur. So that means your 100 rule would basically end up working for this, and you can end up dropping this X and avoiding the quadratic. Okay, so remember, if you do Ka over your concentration, and that's greater than 100, then you're allowed to drop that X. It's negligible because it's going to end up being so small. Oh, sorry, I hit the wrong button. All right, so one other way of calculating acid strength is percent ionization. We'll go through this really quickly because we don't use it too much. So Ka is one measure of acid strength. Percent ionization is another way. So your formula for percent ionization is there. It's the concentration of H plus at equilibrium divided by your initial concentration times 100. So for 1 molar acetic acid in water, we calculated that on your previous example. So your percent ionization would have been your H plus concentration divided by your initial concentration. So if I use the numbers from the last example, the H plus concentration was 0.004. Divide that by 1 and times 100. So you end up getting 0.4%. So that means when this acid dissolves in water, only 0.4% of it actually ionizes and creates those ions. The other 99.6% stays in the solid, or not the solid acid, but in the form of the acid that's not ionized. So here's another one. I'm going to leave this with you to see if you can calculate it on your own. You have to start by calculating the H plus concentration and then calculate your percent ionization. Your final answer, I'm going to give it to you, is 1.09%. So I'm going to leave that for you to do on your own and see if you can get it. If you can't, let me know in class. All right, so now we're going to do the same thing, but for weak bases. So instead of calling it Ka, we call it Kb to indicate a weak base. So here's an example of a weak base. Ammonia, when it reacts with water, makes the ammonium ion and hydroxide ion. So the extent of the ionization, again, you represent it the exact same way. And again, we use the subscript B to indicate that it's a weak base. So nothing's really changed here except we're dealing with bases instead of acids. And again, same rules apply. So when we actually look at weak bases, the larger your number for Kb, the stronger the base it is. So here are 3 bases: ethylamine, ammonia, and pyridine. And ethylamine is still a weak base, but it's the strongest of the 3 because its Kb is the highest of the 3. All right, so let's go through an example when we're actually calculating out some values of Kb. So in this case, methylamine has a concentration of 0.1 molar, and 6.3% of the base has undergone ionization. What is the Kb of methylamine? So at your ionization point, you have 6.3% ionized. So if you started off with 0.1 molar, that means 0.1 times your 63%. At equilibrium, you only have 0.0063 molar of the acid, or sorry, of the base ionized. So if we fill in our chart, we're starting out with your methylamine concentration of 0.1 and 0 of your other stuff. So nothing's been ionized yet. We know this is going to go down by X, and these are both going to go up by X, just like it used to. And how much is it going to go up by? Well, we figured out that because 6.3% ionized, we're going to have 0.0063 molar of it in the end. So over here, we end up having 1 minus 0.0063. So now, hopefully, I've set up your ice chart for you. Let's see again if you can figure out how to actually calculate the Kb. So you're going to use your Kb expression, and you should get a Kb value. I'm going to write it over here, because I'm running out of room, of 4.2 times 10 to the negative 4. So see if you can plug in these numbers that I'm circling down here into your Kb expression and get that answer. If you can, we're good to go. If you can't, ask me in class. Okay, I'm going to do one more example and then I'm going to stop and we'll take up the rest in class. So, calculating pH for weak base solutions. So again, we're looking at the same process as we did last time for weak acids, except again we're starting with bases. So now we have to start, the only thing we have to take into consideration is we have to start by calculating your concentration of your hydroxide ions. Then we can use that to calculate your pH. So, to start off, here is, we're looking at the pH of an ammonia solution. So you have to be able to write this expression out. NH4 plus and OH minus. So your Kb expression, again, products over reactants, NH4 plus times OH minus divided by your ammonia concentration. So in this case, if we were to set up a nice chart and all that, you'd, here I'm going to erase your KB expression, I'm going to write your ice chart in here. So if you have an ice chart, you have, you've got a 0.01 molar solution of NH3, no H2O, and you're starting off with none of this. You know both of your products are going to go up by X, and this one's going to go down by X. Again, this will be 0.01 minus X, X, and X. So now we can plug those into your KB expression. So you end up with X squared on top and 0.01 minus X on the bottom. Your 100 rule is going to apply, so you can eliminate that and easily solve for KB. Now, where do you get, or sorry, easily solve for X, okay? Knowing again that you can get your KB from the back of the book, and it's 1.8 times 10 to the negative 5. So that equals X squared over 0.01. Now you can solve for X. X is 0.00424 molar, and that's the same as your concentration of your hydroxide ions, right? Because we said X will be your concentration of your hydroxide ions at equilibrium. So from that, you can calculate pOH, negative log of your hydroxide ion concentration. So you get 3.37. And then remember that your pH is 14 minus the pOH. So you get 10.63 as your final pH. All right, again, I went through this quickly, I know, because it was basically the exact same process as with your weak acids. We have a couple more examples to go through. If you want to read and try to figure out the last couple examples on your own and go through the summary, you can. But if not, we will do them together in class, so you can wait for that as well. And she's in